This lesson, we're starting our look at calculus, and we're going to start with the differentiation by what's called first principles. Now, before we even start and get into it, we need to do a little bit of background theory. Now, the derivative is also known as a gradient of the tangent at a given point. If you remember, a tangent line is a line that only just touches a graph. So I've just got this equation here, which is x squared plus 2x. So this is just a random, we'll call it a function in terms of x that I've just decided to pick. And if I want to find the gradient at a point, let's say I want to find it at the origin there, the tangent line is the one that just touches it at that point, and I want to find the gradient of that line. That's what the derivative represents. Now, how do we do that? Now, the only way we've looked at gradients so far is find the gradients between 2 points. So I just picked another point, the point 1, 3 on this graph, and if I connect those with a chord, and draw a line through it, then I could find the equation of the line that connects those 2 points if I could draw straight. So as I get my ruler out, I can see as I connect those 2 points, I can find the gradient of that line. And to do that, I'd use rise over run, which is y2 minus y1 over x2 minus x1. And I go, well, let's do that just for this line here. So for example, I could go the gradient would equal, and let's call this 1, 3 can be 0.2. I'd have 3 minus 0 over 1 minus 0, so the gradient is 3. Now that's of the line that connects 0, 0 and 1, 3, but you can see that it crosses the line twice, so it's not quite a tangent. So what I could do then is, well, let's not pick a point that's so far away. Let's move it closer. And I'll grab my ruler, and I connect to those 2 points. And what you'll find is that the smaller the gap between the 2 points that you pick, the closer the line is going to get to the tangent. So ideally, as I move this closer and closer, you can see that the gradient of the line is changing, and the ideal scenario is that I pick a point that is so close to my original value that I'm getting closer and closer to the actual tangent. So what we could say is, let's call the distance here between the two x values, or the 2 points I'm picking, let's just give it an arbitrary value of h. So the function that I started with is f of x, or x squared plus 2x. So I could say that can be 0.1, would be our x value, and whatever the y value of that function is. So in this case 0, 0. And 0.2, I want to just add h to it. So x plus h would be my x value, and the function at x plus h would be my y value of it. So I can use those 2 points, and that just means that any points along here, I can find my gradient by doing my rise over run formula again. So if we go back to our rise over run, y2 minus y1, we'd have, in terms of the original function and the new function to find that extra point that's only h distance away, I could use the formula, the y2 value, which is f of x plus h, minus the y value of the first point, which is just f of x, divided by the x value of the first, also second point, which is x plus h, minus the x value of the first point, which is x, which, notice x minus x cancels off, so I'm just left with f of x plus h minus f of x all over h. And you go, okay, fair enough. I sub those points in. If I put x as, let's say, this distance now, I'm still looking for the gradient at the origin, 0, 0. So in this case, h would be 1. So then when I sub 1 into the original equation, I end up getting 1 squared plus 2 is 3. So then I end up getting this whole thing anyway, when I'm picking a h value of 1. Now, we've already found that gradient, and we know it doesn't equal the tangent just yet. So What we want to find the gradient just at that one point, we want to find out as we get the h value to get closer and closer to our original x value, the h value is actually getting closer and closer to 0. So we write that as this. We want to find what happens to the gradient as h approaches 0. And we can do that by writing what's called the limit. So we're saying, what is the limit of x as h approaches 0 for this equation? So that would be our gradient at the point, or the derivative. Now, in terms of function notation, we do it with a little dash like this. So we'd read that as the derivative of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That by itself is a formula that you need to know. And you see there it is from your textbook. And it looks quite confusing. All I want you to know is that this is just coming from rise over run. So f of x plus h is just your y2 value, minus f of x, which is your y1 value. And you've got h down the bottom because the x's cancel off, as we saw in this step up here. Okay, so let's try and put this into practice for that original equation. We're looking for the derivative for any value of x, and we're going to sub in x plus h into this original equation. So we know f of x from our original point is at the top here. So let's put that in straight away. I've got f of x is x squared minus 2x, isn't it? X squared minus 2x. And what did we do? Plus 2x, didn't we? Plus 2x. Let's check that. Yep, plus 2x. So that's our f of x value. F of x plus h, we just have to sub in x plus h for all the x values. So that would become, instead of x squared, I'd have x plus h squared. And then I'd have plus 2x would become plus 2x plus h. And then it's all of that minus that original function divided by h. So let's try and simplify this down. And the main thing, I keep my limit as h approaches 0 still in there. Okay, looks messy. Still no closer to find our answer. But we've got x plus h all squared. We can expand those brackets and try and simplify to remove any common factors. So x plus h all squared would be x squared plus 2xh plus h squared plus 2 times x plus h would be plus 2x plus 2h. And then we'd have minus x squared minus 2x because the minus is outside the bracket, all divided by h. This stuff follows it down. So let's see if we can tie this up at all. We've got x squared minus x squared, they cancel off. Happy days. Plus 2x minus 2x cancels off. So I'm left with 2xh, and I've got a plus 2h, and I've got a plus h squared. Then I need to divide all by h. So the limit as h approaches 0 of f of, or the derivative of f of x. If we look at this, we've got 3 terms and they all have a h in it. So I can cancel off h there, cancels off 1h from all of that. So the final thing that I'm left with is 2x plus 2 plus h. And so that's a limit as h approaches 0. So what does that mean? That means that if we could sub in a value of h, and as it gets closer and closer to 0, what does this whole red equation here get closer to? And you say, well, if I sub in 0 there, h equals 0, I'm just going to be left with f of x is just going to be equal to 2x plus 2. Okay, so that means that now we have a formula for any x value to find the gradient at a point of our original function f of x. So 2x plus 2, I go up to my original equation now. At any given point on this axis. So at this point here, which is 0, then the function its derivative at 0 would be equal to 2 times 0 plus 2 equals 2. That means the tangent line at 0, 0 has a gradient of 2. If I use the same thing, let's say, well, what if it was at 1? If I put in 1, then the tangent line at that point would have a gradient of 4. If I did it at this point here, which is at -1, I'd end up having 0. And you go, well, there we go. We can see that tangent's going to be at 0. So what we've found is a formula for finding the gradient at any point of the function by using the derivatives by first principle. So for any function whatsoever, we can use this formula here. F of x plus h minus f of x divided by h. And then we're going to use the limit as h approaches 0. The main thing is you go, well, I can't sub in h as 0 at the start because I'm dividing by 0 here. It won't work. You have to expand out, collect your like terms. You notice all these things will cancel off, and you can just cancel off the h's at the end. So now, once you have no denominator, no h in the denominator, subbing in h equals, subbing in h equals 0 into this will work. So you have a final equation. Okay, it looks quite complicated, but the steps are just finding the gradient at any given point. So you just have to plug in x plus h into your original function and then use this formula. Once you've cancelled everything down, sub in h is 0 and you get an equation for the tangent at a point, the equation for the gradient of the tangent, or the derivative. Okay, that's the derivative notation, which you'll see f of x. So that's the function, and the derivative we'd write as f dash x. And you can have any function, g of x, you just write g dash x. If you have a function in terms of y equals something, to write the derivative, we use dy dx. That means the change in y over the change in x. So it's just different types of notation you'll see, but the formulas will stay the same. Okay? Like I said, it does look complicated. It will take you a few goes. Have a go at some of the questions from 17A, and we'll do some worked examples as well.